All right, welcome. So in this video, I want to practice doing some Turing reductions to show that languages are undecidable. So I've created this language that we can use for our example called EQTM. And what it does is check to see if two machines have equal languages. So if M1, it takes encoding two machines, M1 and M2, and it should accept them if they have the same language. We want to show that this is an undecidable language. So to do this, we're going to try and use a reduction, and that means what we're going to try and do, and maybe I'll draw a little sketch over here to remind us how this works, is I'm going to use, or I'm going to try and solve ATM by using my EQTM machine. Okay, so what that means is I have to remember a couple things. What is the input in here? It's an M and a W, but what's the input into here? An M1 and an M2. So somehow I have to transform what I have up here into what I have over here. And my goal is that these machines should maybe have the same language if M accepts W, and these should maybe have different languages if M does not accept W. Why am I thinking that's how I want to set it up? Well, if I can get that relationship set up, then I can prove that EQTM is not decidable because I'll have the relationship I need for the reduction. So let's see if we can go ahead and try that. So I'm going to start by writing the more in-depth proof that EQ is undecidable, and then maybe I'll focus only on the reduction part. All right, so I'm going to start out with my assumption that EQTM actually is decidable and give a name to the machine that decides it. I'll call it Q in this case. And again, remember my goal. So now I've got this machine in here, I'm calling it Q, and I'm going to try and build my machine out here. Maybe I'll give it another name, I'll call it M1. Okay, so I've set up my M1, which is going to take input M and W because that's the input up here, and it's going to try and decide ATM. Okay, so now to do this, this is where the reduction actually usually comes in. Usually down here, I'm going to say something like, write down a new machine M1, where M1 is going to eventually become the M1 here. That's my input to EQTM. Okay. Now, technically in this problem, we need two. We need an M1 and an M2. Now, that's maybe giving me too many degrees of freedom. I really only need one of my machines to do something interesting while my other one is a little bit boring. So what I'm going to do maybe is I'm going to make my first machine M1 be a machine that just accepts all the strings. Okay, now that I've fixed that particular choice, it means I've only got 1 degree of freedom. Now I've got M2, and I want M2 to have the same language, sigma star, if A accepts W, and otherwise have a different language. So I'm going to write down a new one now for M2. Okay, so the machine M2 that I'm going to write now does something very simple. It's just going to, on every single input X, it's just going to run M on W. If M accepts, it will accept. So if M accepts W, its language will be all the strings. But otherwise, if M rejects, it will reject, or if M runs forever, it will run forever. So if M does not accept W, the language of M2 will be none of the strings. So the language of M2, we can write it over here as a little scratch if we want. The language of M2 is either going to be sigma star if M accepts W, or the empty set otherwise. So what does that mean? That means the language of M1 is equal to the language of M2 if M accepts W, and that's exactly what we wanted. So looks like we wrote down the right machine M2. So now we're going to run Q on M1 and M2. Now remember, Q decides if they have the same language, so it's going to tell us if they have the same language, basically telling us if M accepts W. So if Q accepts, we should accept. So this completes M1, which is now a decider for ATM. This is a contradiction, of course, and then therefore that means that we've proven our theorem that EQTM is actually undecidable. Okay, so my argument that this is a decider, I kind of hand waved over here. Instead of formalizing that, we could add a couple sentences in there to make sure that it's clear that this is indeed a decider. Argue that if M accepts W, that we will indeed accept M and W. But if you followed the design with me, you probably can take that for granted as I did. One thing that I want to mention here is that we've used a reduction. The reduction kind of ended up being something like this going on inside here. So I want to go ahead and argue a slightly different thing now. Okay, so what I want to argue now is just that ATM reduces to EQTM. And remember, this is the order we want it in, which is the known one, the one we know is not, is not decidable, to the one that we hope, or the unknown one, the one we're trying to show is undecidable. Okay, so ATM already proven was undecidable, EQTM, the one we're hoping to prove is undecidable. So what do we need to show if we want to show this? We want to show that we can make a mapping between them. So what is that mapping going to look like? Okay, so what's the first part that we need of the mapping? Well, the mapping, we've been calling it lowercase m for mapping. It's going to take inputs that are of the first type, the ATM type, so an M and a W. And it's going to produce outputs of the second kind, M1 and M2. That's what EQTM looks like. So now what we want to do is remember that what makes it a reduction is that we have to link these up in a very important way. And that can be expressed here, that M and W, the inputs that we would get to ATM, if it was in ATM, then that should imply that the output of the mapping will be in EQTM, and vice versa. So I made this an if and only if, meaning also if it's not the case, then it should be not the case. Let's translate this a little bit and see what this means. What does it mean for M and W to be in ATM? Well, that's if M accepts W. What does it mean for these two to be in the EQTM? Well, it's if they have the same language. So the mapping we need to show has to give us two machines, M1 and M2, that have the same language if and only if M accepts W. Well, okay, let's take a look at these two machines. I'm going to say M1 is such that the language of M1 is sigma star. That's easy for us to know that we can build that one. And then let's build M2, just as we did above, because we're following the same pattern. Okay, so my description of M2, very similar to the one that we had above. On any input X, we will run M on W, and we will accept if M does. So that will make sure that our language is the same. So now we have exactly this relationship that we wanted. Okay. We've taken just M and W and shown how we can describe M1 and M2. So we've shown that there's a reduction here. Now remember, from the theorem that we proved in the last video, if you can just show the reduction alone, then that implies that EQTM is undecidable. Basically what we're doing is we're taking the sort of clever important bit, which is characterized here, it looks like on steps 1 and 2, and we're going to strip it out of the larger proof that we have here, recognizing that the rest of the proof is always going to be the same, and we've just focused only on the steps that are maybe going to change for any different languages. Okay, I'm going to take a look at another language here. This is what I'm calling regtm. So we take as input a Turing machine. And now it's our task to determine, is the language of that Turing machine a regular language or is it not a regular language? So what that means is if we want to show that this one is not decidable or undecidable, we need to give a Turing reduction from our known language, ATM. We could use other languages too. We now have EQTM or ETM or HaltTM, all of them. Any known one can fit well here. And we're going to reduce it to our new one, regtm. Now I tend to just use ATM because I know they can all work, and I've just built up a habit and an intuition of how it's going to work with ATM, and so I just prefer a tool that I know how to use it before one that I might have to think a little bit harder on. That's the only real reason why I'm going to use ATM here. And let's think about, like what we said before, maybe taking a little bit a jump down the path here. What does ATM say? Well, we know what ATM is going to be doing. It's going to be detecting if M accepts W. And we want that to be true if and only if, well, this only has one machine here. Let's call this M prime maybe. Okay, language of M prime. And then we're going to say here M prime is a regular language. Okay, so whatever machine we're going to be building here, so remember in our Turing reduction before, what we're going to want to do is we're going to write down what M prime is. So sort of design M prime, and we want to build it out of M and W. Now here's what we have to decide is, well, how are we going to do this? What is it that we want this to be? Well, we want this M prime, we want the language of M prime to either be regular or to be not regular. Okay, we want it to be regular if M accepts W. So we want to be up in this class if M accepts W. Okay, so we need to run M on W somehow and then end up with a regular language. Otherwise, we should end up with a not regular language. So this means we kind of have to decide on some languages, a not regular one and a regular one. And if we can decide on some languages, one of each, then we can probably force M prime to be one of those two languages if M accepts W. Now the languages that I'm going to think about right now, well, I want a non-regular language, and this is the first one that came to mind. 0 to the n, 1 to the n. We showed it's not regular with the pumping lemma. Okay, so I want my not regular language to be this one. Now in terms of regular languages, there's kind of two on my list that I might like. I'm either going to pick the empty set because it's none of the strings, or all the strings because those are both regular languages, and they're very simple for us to design machines for or think about and so on. So this is what I'm going to do, is I want my machine to, I'm going to end up actually picking all the strings because it makes it a little bit easier for me to show my reduction. I'm going to show, I want it to be all the strings if M accepts W, and I want it to be just these strings, only these strings, if M does not accept W. Okay, so what I'm going to do is I'm first going to say on input 0 to the n, 1 to the n, accept. So why do I want to do that? If I accept this string, I know at the very least my language at the minimum is this. All the other ones, if now down here I reject, that's all I have. But if now down here I accept the other strings, I might end up here. That's what I want. So on any other input, what am I going to do? I'll run M on W, and I'll accept if M does. So if M does accept W, then we're going to accept all of the other strings. So that's going to ensure that we have these ones plus all the other ones. That means that we're going to have our language of sigma star. So what have we argued? The language of M prime is going to be equal to sigma star if M accepts W. So it is regular. So we've got the first half of our branch here. And if we want to go the other branch, we just have to argue the same for in the case when M does not accept. And that closes us off, because now what we've argued here is that if M accepts W, we get a regular language. If M does not accept W, we get a not regular language. And so we've shown this if and only if relationship that we were trying to get. So again, by just showing the reduction here, we can now show that regular TM is also undecidable by relying on that theorem that we proved at the end of the last video. All right, thanks a lot for watching these videos, and we'll see you again in that next one.